Hello viewers, Swagadharuna taking you through the story for A-Level Applied Mathematics. And this video I'm going to go through the topic of linear momentum and impulse. So this video is suitable for students in both Senior 5 and Senior 6 offering principal mathematics as part of their combination. Before we start, let's first look at the course outline of this paper. So all these ones are topics which are taught in this paper 2 of applied mathematics. What is ticked is available on this platform, and what is not yet ticked will be uploaded with time. So far I think we realize that statistics and probability is done, numerical methods is done, statics under mechanics is done, kinematics under mechanics is done, and we're left with some few topics of dynamics, and we also finish this syllabus of math paper 2, after which we shall now go to entirely physics. And this video we are going to go through the topic of linear momentum. There are some books which are vital at this level, and these are the ones. If you are doing principal mathematics, there are 4 books. There's math paper 1, math paper 2, term papers with marking guides, and topical question bank. For subsidiary math, it is only 1 book which contains everything, notes and UNEB questions, term papers, everything is in 1 book. Then for physics, there are also 4 books: physics 1, physics 2, topical question bank, and solutions to those questions. So for copies, call on this contact so that you can easily get them at a relatively cheaper price. Otherwise, they are available in bookshops, though at a little higher price. So in your O-level physics, you covered some basics of momentum and impulse, and that's where I shall start from. Then we shall go to what we are interested in. You must have realized that momentum is the product of mass and its velocity, and this is the formula I used. It is the same formula I shall continue using, where mass is the m is the mass in kilograms, v is the velocity in meters per second. So the SI unit of momentum is kilogram meter per second. Impulse is the product of force on a body and the time for which it acts. Note this word, time for which it acts. For example, if a ball hits a wall and it bounces back, there will be that time lag between hitting the wall and bouncing back. That time lag is what we call time for which it acts. Therefore, the impulse would be the force times the time, that time lag. So F is the force and T is the time for which the force acts. Therefore, the SI unit is Newton second. Newton for force, second for time. So from Newton's second law, we realize that impulse is equal to change in momentum, because remember Newton's second law says that the force is directly proportional to the rate of change of momentum, and rate of change of momentum is m in brackets v minus u everything divided by t. So the simple thing I've done is to bring this to this side to come up with ft equal to change in momentum. Then the principle of conservation of linear momentum, it says that when 2 bodies collide, total momentum before collision is equal to total momentum after collision. But there's a condition that there should be no external force applied. Okay, now during this collision, they will have what we call loss in mechanical energy. So in practice, total mechanical energy of a system is reduced by a collision or a jerk. And the explanation for this loss is because some mechanical energy is converted to sound energy of the impact. So the mechanical energy may also be transformed into heat and light energy, leading to a loss in mechanical energy. A perfectly elastic impact, however, in which there is no change in relative speed, is not accompanied by any mechanical energy loss. So we have two kinds of collision. There is elastic collision and inelastic collision. But when they talk about perfectly elastic collision, it means that there is no loss in mechanical energy, implying that kinetic energy before collision is equal to kinetic energy after collision. So like I told you, there are two kinds of collision, elastic and inelastic, and we shall look at both cases. Let's begin with the first case, where two bodies, A and B, of masses m1 and m2, initially moving horizontally in the same direction. So like I told I think you are aware that in vectors, a change in direction is noted by a change of sign. For example, if they're moving in opposite direction, it implies that one will be positive, the other one will be negative. But this time around, the good thing they have told us that they are moving in the same direction. So both velocities will be positive, with velocities u1 and u2 respectively before collision as shown. So let's first illustrate that. Before collision, we have particle A of mass m1 with velocity u1. Then we also have particle B of mass m2 with velocity u2, both moving in the same direction. Okay. After collision, suppose the bodies move in the same direction with velocities v1 and v2 as shown. So that is called elastic because they move with different velocities. So out of collision, you shall have particle A moving with velocity v1, particle B moving with velocity v2. By conservation of linear momentum, momentum before collision is equal to momentum after collision. This G, ignore it. Therefore, it implies that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. That is the principle of conservation of linear momentum. What about kinetic energy? Kinetic energy, just before collision, you get a half m1 u1 squared plus a half m2 u2 squared. So this is kinetic energy for this before, kinetic energy for this before. Then after, it is velocities which will change. So let's see what happens after collision. It becomes this for particle A and this for particle B. If these two are different, it implies that there is a loss in kinetic energy, and to be got by subtraction, the one before minus the one after, which is this. I think you remember something, we talked about something about perfectly elastic. Okay, so if the loss in kinetic energy during impact is 0, that means there's no loss in kinetic energy, it implies that the collision is perfectly elastic. And in this case, the coefficient of restitution is 1. Also, this is equal to this. Initial velocity plus final velocity of one particle is equal to initial velocity plus final velocity of the other. That is what they mean by perfectly elastic. Then the second type of collision is inelastic, where two bodies A and B of masses m1 and m2 initially moving with velocities u1 and u2 before collision. Let's first illustrate that. So we have this particle A moving with velocity u1 and particle B moving with velocity u2. After collision, A gets embedded into B so that they move together with a common velocity. move together, common velocity v just after collision. So that's the second type of collision, known as inelastic. So in this case, they will stick together and they move with a common velocity v. So when we are conserving linear momentum, still linear momentum will be equal to momentum after collision. So the one before will be this m1u1 plus m2u2, but the one after, you combine the masses and multiply by velocity. Still, there could be loss in kinetic energy. So the one before collision is this kinetic energy for this, kinetic energy for this. But after collision, they are combined. Therefore, kinetic energy will be for both masses combined. So you combine the two masses times v squared. Then the loss in kinetic energy during the impact is kinetic energy before minus kinetic energy after, because this after is that. So basically, those are the two questions they ask. Questions involving conservation of linear momentum and questions involving kinetic energy. So for a perfectly inelastic collision, coefficient of restitution is 0, and the particles coalesce. Coalesce means they stick together after collision, and also the separation or relative speed after collision is 0. So v1 minus v2 is equal to 0. That's why we said they move with the same velocity. With that, shall go through these questions. Question 1 came from UNEB 2007, paper 2, question 4, and it says, a particle of mass 2 kilograms moving with a speed of 10 meters per second collides with a stationary particle of mass 7 kilograms. Immediately after impact, the particles move with the same speed, but in opposite directions. Opposite directions. Find the loss in kinetic energy during collision. So shall begin by making a sketch to illustrate the question given. So initially, this particle is moving at a velocity of 10, and the other one is stationary, so it has velocity 0. After collision, they move in opposite direction, meaning this moves backward and this moves forward. So this is backward and this is forward. But they said with the same speed. Speed means magnitude. That's why here you see v and also here v. But in opposite direction, one is moving this side, the other one is moving the other side. So I think you remember we said opposite direction is denoted by a change of sign. So by conservation of momentum, we shall denote it by change of sign. This will be negative and this will be positive. Simplify and make v the subject. So you have got the value of v. Now we have to get the loss in kinetic energy. Let's begin with the kinetic energy before collision. Okay, it before, it is given by that. For A, for B, A, B. The one for B was stationary, that's why it is 0 here. Then after collision, K after, this for A, for B, for A, for B. You come up with that. Therefore, the loss will be got by subtraction, and that's what they wanted. Then question 2 came from UNEB 2023, that is last year, paper 2, question 2, and says, two bodies A and B of masses 6 kilograms and 2 kilograms moving along a straight line with velocities this and that, respectively, collide head-on. Collide head-on, meaning they're moving in opposite directions. After collision, A moves with a velocity of this in the same direction. Calculate the velocity of B after collision and the loss in kinetic energy. So we shall first illustrate before collision, they said head-on, meaning they're moving towards each other. Then after collision, they told us that A moves in the same direction, meaning it moves this side, this direction. And because it moves in that direction, automatically B should also move in that same direction, simply because this is heavier. Then by conservation of linear momentum, we have that. Then we substitute, remembering that change of sign is denoted by a negative. Simplify and get the value of V2, that is the velocity of B. Then they told us to get loss in kinetic energy, so we shall get, first of all, kinetic energy before collision. Substitute for particle A, particle B to give you this. Then kinetic energy after collision, substitute for particle A, for particle B, and output. Then the loss is got by subtraction, and that's what they wanted. Question 3 says particles of masses m2, 2m, and 3m are moving towards each other with speeds 4u and 2u respectively. After the impact, the direction of motion of the heavier particle is reversed and moves with speed u. Find the loss in kinetic energy during impact. So you can make a sketch before collision. That is how the situation was. Then after collision, that's what happened. They have told us the one of the heavier is u. So 3m moves with the velocity u. This one we don't know it, so we shall call it v. Then you can come and say that by conservation of linear momentum, momentum before is equal to momentum after. So you substitute 2m times this plus 3m times negative this, because of change of sign, is equal to 2m times v plus 3m times u. So next is to simplify. We come up with that. Collect like terms. So this m will cancel. Then our collect like terms, 8 minus 6 gives you 2u. This is 2v, this is 3u. Rearrange, you come up with that, implying that v is equal to negative 0.5u. Okay, but they ask for loss in kinetic energy. Now we have left u in the answer because it was given in the question. It is v which was not given, so we had to get its value in terms of u. Then shall come and say that, what about kinetic energy, the one before collision? Shall come up with that for particle A, for particle B, to give you that. Then after collision, we have that for particle A, for particle B, which gives that. Therefore, the loss is got by subtraction, which gives you this. And that's what they wanted. So that was question 3. Now we shall go to question 4, which came from UNEB 2020, paper 2, question 10. And it says, two bodies A and B of masses 3 kilograms and 2 kilograms respectively are 7 meters apart on a smooth horizontal surface. A is moving directly towards B with a speed of 2 meters per second and an acceleration of 0.3 meters per second squared. B is moving in the same direction as A with a speed of 5 meters per second and a retardation of 0.2 meters per second squared. If the bodies collide and coalesce, calculate the time taken before collision occurs and the common velocity immediately after impact. Now, in questions of collision, which we have so far done previously, there was nothing like acceleration and retardation. But now there is acceleration and retardation, meaning that at the point of collision, the velocities will have changed. These velocities will have changed. This one and this one. So we should take note of that. Let's see how it is done. So we shall begin by saying that let B move a distance x before collision. It implies that for body A, it will move x plus 7, the distance it moved. Then the initial velocity is 2, and the acceleration is 0.3, meaning I can get equation in terms of x and t. That is equation 1. What about for body B? Body B, there was a retardation. So it means that's why you see a minus, giving us equation 2. Those are two equations, two unknowns, meaning I can substitute. So when I substitute equation 2 into equation 1, I'll come up with that. Collect like terms to get a quadratic, solve the quadratic, and get the two values. But t will not be negative, so it will be, we shall take this as the value of t. Here I forgot a negative, I encourage you to add it there. Then for part B, the common velocity, so for body A, the velocity now at the point of collision will be 6.2, and for body B, the velocity at the point of collision will be 2.2, meaning that I can now use conservation of momentum. Then I'll substitute momentum for body A, for body B, then the one after which I can now get the value of V which they wanted. Then question 5 says a bullet of mass 100 grams is moving downwards at 30 degrees to the horizontal with a speed of 500 meters per second. When it strikes a wooden block of mass 1 kilogram, which is lying at rest on a smooth horizontal table, the bullet penetrates the block and moves and becomes embedded in it. Calculate part A, the common velocity of the block and the bullet after the bullet has come to rest relative to the block. Then the impulsive reaction of the table on the block. So shall make a sketch. That is the body resting. Then the bullet is at an angle to the horizontal, and that angle is 30 degrees. Then after collision, the bullet gets embedded, meaning that now the new mass increases is the total mass of this and this. That's why you see a 1.1 kilogram. So by conservation of linear momentum, this one, it has been linear in the straight line, so we are going to resolve this to the horizontal. That's why you see a 500 cos 30, and this will be the mass. For this one is initially stationary, so it is zero moment. After collision, it's combined, m1 plus m2 times the common velocity, and after that I can get the value of v. After getting v, that's what they wanted. Part A, part B, impulsive reaction on the table. Impulsive reaction will be the vertical component of the momentum of this bullet. So when I resolve this velocity vertically, I'll come up with this. Then I can substitute and get the reaction they want. Then question 7, it says a particle of mass 0.2 kilograms and velocity this in vector form collides with a particle of mass 0.3 kilograms and velocity this in vector form. If the particles couple together, find the kinetic energy of the particle after collision. So we can remove this S after collision. So by conservation of momentum, now we are dealing with vectors. That is why you are seeing these tildes. Then you can substitute and simplify. This multiply with this and this to give you that, this with this and this to give you this. and these two add to give you 0.5. Simplify further and then take this 0.5 this side to come up with that as the velocity. But they wanted kinetic energy, so kinetic energy after collision will be this. Now here in vector form, we can't just put we can't square a vector. That's why we first put a magnitude. And that will be the answer they wanted. So that was elastic and inelastic collision and energy losses. Now you're going to what we call recoil of a gun. So when a gun is fired from a gun, when a shot is fired from a gun, an explosion occurs in the barrel of the gun. The explosion takes the form of expanding gases, which exert a force on the shot and an equal and opposite force on the gun. Initially, the shot and the gun are at rest. Note this, meaning momentum before is 0. The gain in momentum of the shot after the explosion will be equal and opposite to the gain in momentum of the gun. So in a horizontal direction, therefore forward momentum of the shot is equal to backward momentum of the gun. So let's first illustrate that. That is before explosion. Then after explosion, the gun jumps backward and the bullet goes forward. So this one has a forward momentum and this one has a backward momentum. Therefore, before explosion, since they are at rest, it implies that momentum is 0. Then after explosion, the change of sign, I think you remember, different directions denoted by change of sign. You come up with that. By conservation of momentum, we shall equate the two and come up with that. That means that M1 V1 is equal to M2 V2. So with that, we shall go through these questions. Question 1. A bullet is fired from a gun with a horizontal velocity of this. The mass of the gun is 3 kilograms and the mass of the bullet is 60 grams. Find Roman 1, the initial speed of recoil of the gun. Roman 2, the gain in kinetic energy of the system. So let's first illustrate. That is before explosion, and after explosion, this one jumps backward and this one moves forward with a velocity of 400 meters per second. Therefore, by conservation of momentum, we shall come up with momentum before explosion being equal to that after explosion. This is 0, and this is positive, this is negative. So I can get the value of V, and that would be the initial speed. Then next, they want gain in kinetic energy of the system. So initial kinetic energy is 0, and final kinetic energy is this for the bullet, this for the gun, to give you that. Therefore, the gain will be got by subtraction to give you that, and that's what they want. Then question 2 says a gun of mass 5 kilograms fires a shell of mass m horizontally. The recoil of the gun after explosion is opposed by a force F, which brings it to rest in t seconds. Show that the energy of the explosion is given by that. So you come and first illustrate before and after. The gun jumps backward, this one goes forward. So from Newton's second law, just after explosion, we have that negative because it is opposing, meaning that acceleration is this. Then when the recoil of the gun comes to rest, V is equal to U plus e.t.c, where V is the final now, initial at the point of recoil, then acceleration and the time it takes. Therefore, V1 will be given by that. So before explosion, both the gun and the shot are at rest, and the total momentum is 0. Therefore, by conservation of momentum, momentum before is equal to that after. So substitute before is 0. After there is this, I think you know why we're putting negative, giving us that. Then we can substitute for M, for V, M for V. Therefore, V2 is equal to this when I make it the subject. Therefore, energy of explosion is the total kinetic energy initial minus final. Final minus initial, which gives this and that minus 0. So come and substitute. M1 is that, V1 we already saw it, M2 is that, V2 we got it. So next is to simplify and get the required expression, get the LCM, collect like terms, and this is what they wanted. Question 3 came from UNEB 2012 paper 2 question 16, and it says a gun of mass 3000 kilograms fires horizontally a shell at an initial velocity of 300 meters per second. If the recoil of the gun is brought to rest by a constant opposing force of this in 2 seconds, find Roman 1, Roman 1 the initial velocity of the recoil of the gun, Roman 2 the mass of the shell, Roman 3 gain in kinetic energy of the shell just after firing. And part B, Roman 1 the displacement, and Roman 2 work done against the opposing force. So let's begin with A Roman 1. So the sketch is that before firing and after firing, just backward, and this one moves forward. Okay. So if a constant force F brings the gun to rest in 2 seconds, it must exert an impulse equal to the initial momentum of the gun. So impulse is equal to initial momentum of the gun, Ft is equal to M1 U1, where this is that, this is that, this is that. Therefore I can get my initial velocity. That was Roman 1. Roman 2, they want the mass of the shell. So before firing the shell, the gun is at rest and the total momentum is 0. Therefore, by conservation of linear momentum, we shall come up with this initial and after, before and after. I think you know why we put a negative here. Then substitute for, we already got U1, it is there. And now I can get the M2. Then Roman 3, they wanted the gain in kinetic energy of the shell just after firing. So gain in Ke is equal to this minus that, where we substitute that and this to give us as the gain in kinetic energy. Then now shall go to part B. Displacement of the gun and work done against the opposing force. So we shall come and see that from the first third equation of motion, this final initial acceleration, we can now get the displacement, which gives us that. Then for work done against, the resistance is force resistance times displacement. We already know that the resistance is that, displacement we have got, so we can come up with the work done. And that's what they wanted. Then question 4 says a gun of mass this fires a shell of mass this and recoils horizontally. if the shell travels along the barrel with speed this, find the speed with which the barrel begins to recoil if the barrel is horizontal, and 2, if the barrel is inclined at an angle of 30 degrees to the horizontal. State in each case the constant force required to bring the gun to rest in 2 seconds. So before firing is that, and after firing, this one jacks backward and this one moves forward with a relative velocity. So this is v1 minus this, meaning that this velocity is reduced by that. So the resultant velocity of the shell as it leaves the barrel will be this minus this, which is here to the right, and this is because the barrel is recoiling with a velocity v1. So before firing, the shell and the gun are at rest, meaning total momentum is 0. By conservation of linear momentum, we shall come up with that before and after. Expand, collect like terms, put v1s on one side and v2s on the other side. Then v1 will be equal to that. But they said they want also the force. So if a constant force F1 brings the gun to rest in 2 seconds, it must exert an impulse equal to the initial momentum of the gun. So impulse is equal to initial momentum of the gun. Impulse is this, initial momentum is that, which gives you substitute for time, and you'll be able to get the value of F. That also Roman 1. Roman 2 is when the barrel is inclined. The barrel is inclined at an angle of 30 degrees to the horizontal. So we shall come and make a sketch again before firing and after firing. So it moves with that velocity, but is still opposed by the recoiling velocity. So the resultant velocity of the shell as it leaves, we shall resolve horizontally. This is because the barrel is recoiling. Then before firing, the gun is at rest, therefore total momentum is 0. By conservation of linear momentum, we shall come up with that. Substitute, collect like terms, and make v1 the subject. Therefore, the initial velocity of recoil is that. But they also wanted the force. So let F2 be the force which will bring the gun to rest in 2 seconds, meaning that impulse is equal to initial momentum of the gun. Impulse, initial momentum, you come up substitute for the time, and this one goes inside, then you'll come up with the value of F2, and that's what they wanted. So question 5 says a 2-stage space rocket is cruising at a speed of this when the stages are separated by an external explosive device. The smaller stage, which has a mass of 1 ton, then moves away from the larger stage, which has a mass of 4 tons, with a relative velocity. I think we already covered relative velocity on this platform of this. The direction of motion being unchanged. Okay. Find the velocities of the stages of the separate stages. So you shall come and say that relative velocity is given by that expression. Then come and substitute relative velocity was 100, meaning I can now make V2 the subject. Then you can use conservation of linear momentum. Before collision it was that, after collision they were now split into two, one for 4 turn, another one for 1 turn. But I know V2 in terms of V1, so come and substitute for V2 in terms of V1. Then simplify to get the value of V1. After getting V1, I can now get V2 from here, which is that. Therefore, hence after separation, the smaller stage moves at this, and the larger stage moves at that. And that's what they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on elasticity. So still, if you're not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so you can all benefit as a family. Otherwise, today is 31st December 2023. I wish you a happy new year. So tomorrow shall be in 2024. All the best.